this in your patent?
So that was never intended by Fisher to be the case, but you know, that's how people started to use it, and because there's so much inertia in science, it's never going to go away, or at least for a long time. There's a psychological journal, I think it was APS, or I can't remember which one. Someone in psychology would tell me which one. We actually started to ban p-values. They said, now we don't want to see any p-values anymore. You have to describe your result in other ways, and I'll show some of those other ways in this further. So there's this I think Johnson does the in PNS in 2013, so not that far ago, started to think that okay, p-value are not really good, and one of the reasons is that if you look at the p-value versus the evidence as a that's the problem. The problem is that the p-value is not a measure of evidence. And that's how people use the p-value. They think, okay, if my p-value is very small, and I'll explain why it's not a measure of evidence. If my p-value is very small, that's an evidence for that I've got some my alternative hypothesis is probably true, and that's not the case. So they look at the evidence versus the p-value and say, like looking at base factors, and they're thinking, okay, for that kind of p-value, what kind of base factor do I have under some reasonable assumptions? I think Russ showed that thing, right? Yes, I mean, so I won't go too long in that. But basically, they suggest that after those reasonable assumptions, they suggest that the p-value of 0.005, for instance, would be a better way, or 0.005, 0.009. It depends on 0.01. It depends on the assumption. So there's no threshold, and again, there's no threshold in real life, right? It's not because there's no threshold except that you have at some stage to take a decision sometime. Sometimes when it is in the framework of decision making, then a threshold makes sense. So you have to think, is my study something about decision making? Do I have at the end of it to take a decision? Do I, for instance, give that drug to this cohort, or do I not give the drug? Like that's a decision-making process. For a decision-making process, a threshold is entirely variable. Now, if you're in science and you're thinking, okay, do these data actually show something about that hypothesis? There's no really decision. It's either they're kind of like a reinforce that hypothesis or the opposite, right? And there's no strong. I mean, you're not going to make an entire decision. You will need more experiments and more things to happen. So, anyways, so evidence of reproducibility, I won't go into that. You except to show that figure, which I think is fantastic. Yeah.
Can you reach this link?
So it's both on the Neurohackweek repository. I think maybe it's called Power. I can't remember. It's a repo. You can clone the repo. It's also on my GitHub account if you, yeah. So that figure you should all know. Because that figure is, I think that's Molenjink, 2012. There's a couple of exactly the same sort of figures. You can find other, meta-analysis. So that's a very interesting one. So on the x-axis, you've got the year of publication, and on the y-axis, you've got the effect size. And I'll go quickly of what is the effect size, but basically the amount of signal that you find in your experiment. And the circles are representing the size of the cohort that were the sample size. So the bigger the cohort, the bigger the sample size, the bigger is the circle on that figure, on those. I can't remember what are the dotted versus non-dotted one, but basically what happened is that the early on, 2004, 5, and so on, you've got dots a little bit all over the place, but some of them are quite high. So you get high sample high signals, right? High effect sizes, and then people start to get more like a larger cohort, and then the sample size, the effect size diminishes, right? And that's that's not uncommon. It is not uncommon. So each time biologists, psychologists, life sciences people get a study that has an effect, and it could have a very high p-value, I would say a very small p-value, very significant p-value. They usually get to sometimes high-profile publications, journal, and that makes a buzz. And then because that makes a buzz, people start to try to replicate, and so on. And not always, but not that rarely, we get the phenomenon that the sample size is going down, and that's the winner's curse problem that I will describe. So before going. So you know about Ioannidis, and you know about so a lot of the things that Russ presented is in this notebook as well. So if you don't have his slides, just maybe one thing on the Simonson and Simonson paper, the flexibility of analysis. So that's a reminder of the flexibility and the p-hacking problem. So p-hacking problem, you maybe already know. That's the fact that we don't, classical statistics don't have a test and a trend set, and therefore they don't. And they should, and that's something that maybe hopefully will be going in the literature more and more. But if you play with your data, as soon as you look at your data, you are impacting your inference power. And it gets really complicated to, let's say, I'm not going to look at all the data, I'm just going to play a little bit or look at some summary statistics of my data. How much power did I lose in that process? And that's a very complicated thing to compute. Because you have now an inference that is conditional on anything that you have looked at, right? So having that very clearly in mind, and going through what Russ was saying on the pre-registration is completely critical if you want to at some stage take a decision and do inference. You don't have to do inference. You just have to describe what is inference, and what is not inference, which is hard, especially in the life sciences domain, because there's such inertia in the way things are accepted and presented in the publications. So I just want you to point out that number, which is those are analysis of classical, I think, reaction times, classical data in psychology, and they did a survey. What do you do this sort of procedure on your data? So they looked at the survey of do you add sometimes more observation when tests are not significant? Do you control for gender or interaction for these sort of things? And so they looked at what is the classical way of analyzing the data. And they put all those classical ways and say, okay, see, if you do all those things, at the end of the day, if you try to combine situation A, B, and C, and D, right, you get something like 60% false positive rate. So it's not at all of the order of the 10% that you may get from the random field theory cluster-wise. Right? It's not the same order, right? It's something which is way more problematic than this kind of, or even the Afni bug, which is, I think was giving maybe 11% false positive rate or something like that. So we have to think of what are the big problems. And what are the small problems? One of the big problems is the p-hacking, right? That's a big problem, and that's the usual. I mean, you've seen Russ Karp et al. And you can get basically activation wherever you want if you try enough procedures and enough pipelines. So the big problem is the p-hacking. A couple of corollaries. So I'm now going to give you a little questionnaire, and that's a classic questionnaire. So consider a typical medical research study. So, for example, designed to test the efficiency of a drug, in which a null hypothesis, there's no effect, is tested against the alternative hypothesis, there is some effect. Now suppose that the study result pass a test of 0.05%, and you ask what has been shown. So the question is, so first H0 is false. So how are you get all the sort of the question, and then you will show me a hand with the number you want to so you show me 3 or 4 for the thing you think is right. So did you show that H0, the null hypothesis, is false, or that H1 is true, or that H0 is probably false, or that H1 is probably right, or both that H0 is false and H1 is true, or both that H0 is probably false and H1 is probably right, or none of the above? You haven't shown anything. So I'll give you maybe 10 seconds, and I'm sure that some of you have a statistical training and they know the answer. So okay, so don't shout the answer, but you just to have a a little thought about that. So you've got your statistical test. It's less than P0.05. What did you show with that p-value? So any all the way hands up. What? Don't be shy. Don't worry. I'm not going to. This is not recorded. This is okay.
I got it.
Okay, 3. You've 7. You're 6. You're 6. You're 3. You're 7. You're 7, 3, 6. Okay, so you're all probably reasonable scientists, and still there's kind of a half split. People. I think a good chunk of people say 7. There's nothing has been shown of what is there, but a good chunk of people would say 6. Some would say 3. It's unclear what the p-value is in general, and you're better trained, and you're probably way more better trained than the life science in general. And so this questionnaire was given to medical students. I think 80% of those students, or 85% of those students, who are actually using the p-value for their practices in terms of deciding or whether I'm getting this is good information for a drug or not. They're actually using that tool quite a lot. 80% got it wrong. So the true answer is the right answer is none of the above. You can't actually. And first of all, you have to think of what is probably false or probably right for hypothesis, right? What does it mean for hypothesis to be probably false or probably right? It means that the hypothesis is something that is random. Right? You have to associate with the hypothesis a random aspect, right? The randomness aspect is, the random is when you have a series of hypotheses the hypothesis is not random. It's either 0 or 1. You can probabilize it. You can attribute to it some likelihood or but the hypothesis in the classical setting it's just not a random thing anyway. So it's even this formulation is really bizarre in that thing, right? And I'm sure Jeanette will explain that better than I would. But it's so basically that tool is really misused and not understood. And the reason why it's not probably false or probably right is that let's say you do have something like a random hypothesis, or let's say you associate some confidence or some randomness in it, so therefore you're getting into the Bayesian framework. If you do this, then you have to know what is the original prior that you have to say to that. So if I have a very significant test that pigs can fly on my experiment, right? But my prior is that pigs usually don't fly. I've got a very strong prior that that's not the case, right? The answer is that probably still the hypothesis is still probably false, right? Whatever is the answer of the test. So you have to think in terms of prior. If you think of what is my hypothesis HGO or H1, is that right? Or is it true or false, right? And that's a very important thing. Let me think. Where am I? There's another good paper, which I think I want. What's the time now? Okay, so plenty of time. There's a very good paper showing it's called the dirty dozen of the p-value misconception. So you have a quick look at that. Maybe some of those misconceptions are quite interesting. And they basically all turn around the same problem, and because it's not a very clear problem, it's a difficult concept. The p-value, like the probability of the result that I observe given my null hypothesis is not something that is straightforward, and because that concept is not very easy to get. You get a lot of misconception, and all those things are some of those misconception. So let me think if I can think of a good one. I think the number 12 is important. Like a scientific conclusion of treatment policy should be based on whether or not the p-value is significant. That's absolutely wrong, and I just want to reinforce that because that's unfortunately sometimes what is happening. So. I would also point to you, and again, all those references you get access to to the fact that because I will show later. No, maybe not in that notebook, but it is possible, not that difficult, to show that a p-value is uniformly distributed on the null. So if you are under the null hypothesis, you are the same probability of getting a p-value of 0.001 to p-value of 0.09, right? It's the same. Any p-value is as likely as any other under the null, and I can show you that on the board. It requires a little bit of fudging with a cumulative density function, but it's not that complicated. It's really like only a few lines. And so, therefore, it can never indicate evidence for the null. I think if you think about that, it's just like a straightforward, right? Because it's completely uniformly distributed on the null, it doesn't show you any evidence of the null, right? But that's something that is not, again, that's something a little bit counterintuitive. It's not very clearly thought by people usually. So let me skip the other. So I've shown you 3 papers about the misconception of p-values. There's the Westover paper, there's the Johnson paper, and then there's the Goodman paper. So all those 3 papers, when you read them, you don't think they say that you will recognize some of the things. They're not. It is hard to read those things and put that in the same framework somehow. And therefore, that's why I think the p-value is so badly used. Is that it is so even people are thinking a lot about those things are still thinking it differently with some kind of different way of thinking of it, right? And that's the hard. And that's why you have to read all those things until you sort of get your own perception and get your own your own logic and your own understanding emerging. So let's go to the notion of power. I'll have to get a few definitions on the way before I can do this. So let's call HGO the null hypothesis. So I'm going to assume that all of you know what's the null hypothesis and alternative hypothesis. But yeah, okay. I was assuming that. I hope and anytime I'm I know we've got different backgrounds, so anytime there's some question, please, it is time to ask question. So null hypothesis, okay, that's the alternative hypothesis that it's not the null. That's all it is. Test is significant, test not significant, so that's the result of the test. And alpha is the false positive rate, so the probability to reject H0 when it is true. So let's say I'm sampling on the noise distribution. Sometime I will have, if I take a decision at alpha, sometime I will get some alpha less than 0.05, and I make the decision, I make the wrong decision that I can reject the null. So that's alpha, and beta is the false negative rate. So that's probability to accept H0 when in fact the alternative is true. Why are we always looking at alpha and not beta, which sounds to be like a very important false error rate, right? Is going to be hopefully become clear, but it's one of the big problems. We're always looking at alpha and we're not looking at beta. And so if you're rejecting the null, but if you're the probability of accepting H0 when HA is actually true is very high, what does it mean? And that's the thing we have to think about, and hopefully that will become clear. So the power is 1 minus beta, so 1 minus the false negative rate. So that's the yes. So it's basically 1 minus is the opposite of the risk of false negative, right? So it's the probability of getting the alternative. Probability of getting alternative. Okay. So the problem is that to compute the power, we need to know what is the risk of false negative, and this risk is not the risk to show that there is a significant effect while we have some signal. The null is false, right? So what I want to say on that? So that's the problem, that we need to know the risk of a false negative. So how do we compute the risk of false negative? How do we compute beta? That's a little bit annoying. So I'm going to show now some, and the real problem is that we need some information of the effect size of what is our signal, and we need some information of the distribution of that signal, and which things that often we don't have. Why is that interesting? So let me just run that. See. Okay. So this is just a table. So that code is just it's a horrible code to display a table using LaTeX formula. And I'm sure there's a better way of doing it. Someone we know, like if Dan or Satra or someone knows those things, they will show me some better way of doing it. But anyways, that's using the SideByStats package, which will allow you to sort of do some symbolic computation, but also have a display aspect to it, which therefore we can display those things easily. So 1 minus beta will be 1 minus beta, like that, and so on. So look at that. I don't want to go in that little thing. That's something that's very important here. So that table is the critical table. So we have hypothesis and test. So on the lines are the rows are the hypothesis, the columns are the test. So rows hypothesis alternative, the test is significant. What's the probability of that? Significant when the alternative is true. It's 1 minus beta, and that's the power. That's our power. When the test is negative, that's our risk of error of type 2. And when the H0 is true, if the test is positive, that's our risk of error of type 1, alpha, and 1 minus alpha for the when the test is negative. So how do we compute power? So I'm going to take a very simple example And first of all, I will look at what is the effect size. What do we call an effect size? In this very simple example, my effect size is just the difference between two means. I've got two groups. I've got that are sampled from two populations, and those population means they're not like the average of my groups. They're just the actual population means are different, and I've got a difference which is this my effect size. The Cohen's d effect size is that difference between the means of the population. So I've got, let's say, I'm taking the size of the brain of a schizophrenic, or the size of a structure in schizophrenia population, and the size of the structure in the normal population, and then I look at the difference of those sizes. But I now divide by the variation of the my sample data. Right, so depending on if you're, I'm not dividing by the variation, the standard deviation of the means of the sample means. I've divided by the standard deviation of the data, right? So that's the standardized effect size. So if you have to think a little bit of sometimes it makes sense, sometimes it's less sense, and what does it mean to divide by the standard deviation of the actual data? And again, not of the mean, right? Well, it means that, again, it's just a way of being able to compare effect sizes between different situations where, sometimes the situation is, you have very large standard deviation, so the difference doesn't mean that much, right? Or if you have so it's just a way of comparing effect sizes between population, between situations. It's a normalization factor. The problem is how do you estimate that normalization factor, and I'm not going to do that. Now, if you account for the sample size and and forget about the degrees of freedom, and if you look at just the a basic aspect of the z, what you would compute as a z variable, then you just have to divide by the square root of number of the data that you have, right? It's roughly, again, I'm not talking about the degrees of freedom, let's say. So there's a very simple relation between the z and therefore often the p-value. Let's say if you assume a normal distribution, so z p-value would have a one-to-one mapping between, and then there is a very simple relation to how you get to the effect size, right? In simple situations, and there are complex situations where it's going to be much more. But in simple situations, so effect sizes can be. In this instance, I've taken a very simple example of the difference between two means. They can be about anything. So a correlation can be an effect size. So amount of variance explained can be an effect size. Someone give me another example. All those. What is relevant in terms of what is relevant for you as a researcher for your experiment can be an effect size often. Jeanette, you think of another?
I wasn't paying attention. Did you say percent signal change already?
Percent signal change is an effect size.
Whatever that is.
Whatever that is. Yeah. So and then percent effects, so the percent chance would something be close to that effect size, right? Then if you want to have something which is closer to a Cohen d effect size, then you would have to think, okay, what's the variation of my bold data, and then correct for that. Okay, so now we have a vague idea, hopefully not too vague, of effect size. So this is a simple where I want to look at this mu parameter, and then I look at what's the Cohen d effect size for various means differences and various sigma for my data. Okay. Just for those who have not been using NumPy or SciPy or this is I think there's nothing there to look at very much. Okay, there's no. I'm just dividing my mu by my sigma, and that's it. And in the psychology literature, you would find that an effect size of 0.4 is a weak effect size. A point maybe 5, 6 is getting to be a strong effect size. Is that right? 0.7 is really strong effect size. And so if you go on Wikipedia, look at effect size, Cohen's d effect size, you would have some sort of a range of what people think in some, but it's completely field dependent. It doesn't have, don't trust those Wikipedia pages in some sense, because for your experiment, maybe a 0.2 is a very strong effect size, and there's no way to know until you have the experiment. I mean, you have the experience of several experiments in the same domain. But it is still an interesting scale in the sense that because it runs between 0 and 1, and your basic, if you have an effect size of 0.9, you know that this is such a strong signal that there's. I mean, you just have to know that's a very strong signal. If you have an effect size of 0.05, you just have to know that's a very weak signal. But there's no other absolute aspect to that, I think. So now you have to estimate the effect size mu, and some under sort of normal. So we have to estimate that. So how do we estimate those things? Well, it's I guess the classical way, and I'm not going to do an entirely stat course here. So, but basically, typically your t-value would be an estimation of your effect size non-normalized on the top, and then divided by the standard deviation of that effect size estimation, and that has some aspect of the variance of the data in it, and some aspect of your sample size, right? Using that formula. I mean, something similar to that in more complex cases. But, okay, so now we're still on the way of computing power. So power is the probability that the observed t value, that this is our statistic, we're computing that t value is greater than that the t at the 0.05 for the null, so that you compute assuming that you have no signal and you are under the null. So you compute t under the null at 0.05, and then you want to compute the probability that t is greater than that. The problem is that we want to compute the probability that that t here is greater than the t under the null, right? So for that, we need the distribution of our measured t, and that's the problem. Now, what the heck is that? So we therefore need to know the signal and the effect size for that, right? So now let's assume that we know that we have this distribution, and I'll call it T NC for non-central, and there will be a good reason for that. And then the power will simply be 1 minus beta, which will be the probability of T being greater than 0.05, which is 1 minus. So I'm guessing that you know a little bit of stats, and I'm not losing anyone if I say that the probability of t, so that variable that if I was to repeat the experiment under the same experiment many times, that variable would have like that random variable t would be what is the probability that random variable t is greater than this threshold t computed at p equal 0.05 under the null. So if that probability is 1 minus the cumulative distribution of this variable at that t05 value. Is that losing someone or not? Maybe I can. Guys, you have to say something. If you don't say anything, I will consider that I'm losing you. No, you're lost. No, everyone is okay. Oh, you're good. Okay, so that's a very simple thing. But what does it show? It shows that the non-standardized the power depends on 4 things. Yeah, and I don't think, like if I asked you before what the power of an experiment depends on, like I'm not too sure you would have those 4 elements, right? You need the non-standardized effect mu, you need the standard deviation of the data sigma, you need the number of subjects, so the sample size, and you need the type 1 error of risk alpha, right? So that in that setting, you need those 4 things to compute the power. Yeah, there's no way out of that. Right, you need your threshold alpha, you need the number of subjects, you need the standard deviation to need to be able to compute those the standard deviation of your data, and you need to the standardized effect mu. So so once you have those things, and you almost never have those things, can I just move that thing a little bit? I'm using this fancy Jupyter extension that I think was shown by early on, and I think it has reduced my window enough that it's actually hiding things now. But so once you've done the things, you can compute. Once you have those parameters, and you also need the distribution of your effect, right? So now you have to think that your experiment is going to give you an effect, and then you have to know that distribution of the effect to compute that probability here. So that cumulative function here. So again, that here I need the distribution of t, which is my the statistic I compute under the effect of that specific effect, right? That the alternative hypothesis. Right. So okay, let's do this. How do we do it? Well, if you look at exactly what is the this thing here. And if you think that mu here is not 0, it is 0 under the null, it is not 0 under the alternative hypothesis, then you look at the distribution of that thing, and you, by sort of asking a statistic friend or a statistical friend, or asking Wikipedia long enough, or you will see that this is distributed as a t distribution, which has a non-zero parameter. Instead of a central 0 mean t distribution, it has a non-zero t distribution. So it kind of shifted t distribution towards that parameter. And that parameter is the non-standardized effect size, or the standardized effect size multiplied by the square root of n. And that's easy to see somehow. That if you look at that formula somewhere here, if mu is actually not 0, that would be your parameter, your non-central parameter for the t distribution. All right, so this is a little bit unwavy, but still, this parameter, when you can simulate a non-central t distribution and say this is my what I would get as an experiment under the hypothesis, the alternative hypothesis, and look at what you get from that. So let's do it. And how many of you have used SideByStats before? 1, 2, 3, 4, maybe half of you, maybe a third of you, given that most of the Dan, I don't count you as a you've done too many studies on that. But so I'm looking at SideByStats, which is a great package. It's a little bit confusing to work with, to start with, but you will see by just a couple of examples how I use that, and that's a very useful thing. So this is computing the power And again, to compute the power, you need the mu, the non-standardized effect size, the sigma of the data, the alpha, the threshold at which you're going to take the decision, and this is just a plot to look at the plot, and those are the way you define the. I mean, it's a good way of showing. It's a bit like the NumPy way of describing your parameters. Is always a reasonable thing to do if you're writing a function. So function is not very interesting, except that I want to go exactly over. This is my non-central parameter, my t, this non-centrality t parameter. So that's just what it is. Looking at the formula, and this is how you use SideByStats. You actually create a random variable. And what is this random variable? This is non-central t. It has a number of degrees of freedom. It has a non-centrality parameter. So now that non-central t random variable can be used for anything. So for instance, I can ask here, what is the CDF of the cumulative density function of that non-central t variable? Or you could ask the PDF, or you could ask the survival function, or you could have the inverse survival function. All those things are attached to that now variable, or you could ask to generate data from it. So that's a very, very useful package that so in this instance, I create that variable. Here I look at the power, and that's 1 minus the risk of error of type 2, and which is the cumulative density function at the. I could actually have used the inverse, the survival function, but whatever. And this is the t value at which I'm going to threshold and decide, which is not the central t, it's actually the t statistic here, and I'm taking the inverse survival function, which goes from basically alpha values to t or z values, depending on what distribution you are. So if instead of a t here, I had the normal distribution, I would have from the alpha to the z value. Okay, and I really should draw things on the board. Yeah. So again, the CDF, just like this part. If you look at the t, and if you look at so that would be like the CDF would be that part, and the survival function would be the other part. The inverse survival function. No, the survival function. Yeah. So this is just a plot. What nothing really to show. I'm just like this is going through the plot to look at to try to plot those two distributions, the null distribution and the alternative distribution. So that's how it looks like. What is happening here? We've got our null hypothesis centered on 0, and we've got our alternative hypothesis centered on that theta parameter. And that bar, that red bar, obviously is the at the moment where you cross the t value that corresponds to a p value of 0.05. So power is simply the amount of that alternative distribution. So it's again, power is always going to be computed with the alternative. Okay, so you have to know the alternative or to assume the alternative. And for that specific alternative distribution, this is the power that I would have, and which is in this case 80% or 83%. So that's pretty good. This was with n equal 30. Mu equal 0.5 and sigma equal 1, right? So that's my setting. You have to sort of know the distribution, the number of subjects here, 30, the number of what's the effect size and what's the sigma. So now let's try with mu equal 12 and see what happens. Well, obviously the sampling distribution is wider. Our error on the sample mean is wider, and the power decreases as that happens. And you look at that through just the non-centrality parameter, because it's got this square root of n. You would just follow that square root of n is the thing that is driving the power. All right, so we've got yeah.
So the mu here is your let's say your percent signal change or whatever.
Exactly.
But
So,
how is the sigma defined? Like normally I would say I have an effect of like a 10% change, and then I have a 5% standard deviation on the mu. Let's say, like if I have two groups, I know there's a 10% change in signal, and each of those mu's I measure with a 5% error. So.
Right. So the 5% error comes from two things, right? If you have an error on the estimation of your effect size of your mean, there's two elements in that error, right? There's the first element, which is how noisy are the data, and the second element is how many data did you get.
Oh yeah, so I mean actually in order to estimate exactly when you normally do like number of subjects, like sample size estimation, you give parts of this too, right? You give normally the mu's of the groups, you give what kind of measurement error you expect, and you give what kind of type 1, type 2 error you allow, and then you calculate your n that way when you do sample size calculation.
When you do power computation,
Exactly.
yes, you exactly, yeah.
And
so the question is how do you know the sigma, right?
Exactly.
Yeah, and that's the sigma of the data.
Yeah, so this should just be your
Right.
noise measurement.
That's the noise measurement. So often what people do is that I don't know the sigma, but I have a vague idea of the Cohen's d effect size. Okay, so what happens is, and I think you probably show tools after that, Janet, on that problem, right? For power computation. No? I can't remember.
During my talk?
Yeah.
No, I'm just doing efficiency, so just the...
Oh, efficiency. Okay, so it's a slightly different topic. So yes. So let's say you want to compute power, and you go on the web and you have a power tool, and there's a number of those, and there's a number of those actually, one by Janet for fMRI and one by Yoko as well. But basically you don't usually know the error of your. You just assume that what you know is normalized by the error. So if I say 5% effect change, I would probably assume that the sigma of the data is 1. Right.
You say 5% change in sigma is what?
And you would assume that you don't have like these two information. You don't have the information of the how much noise do I get and how much changes of signal do I get. That's why the Cohen's d is important and useful, because you just collapse those two things in one number, which is how much did I get. I'm not saying that the effect size non-normalized is not important. It is crucial to look at as well. It depends on the situation, really. I mean, for fMRI signal, for instance, that's not that crucial in the sense that the noise will depend on so many things: normalization, the scanner, all those things, right? So for that thing, I think the Cohen's d effect size is actually a better measure of what is the effect size. It is normalized by the amount of noise that you have, right? And the amount of noise is being the noise of the data themselves, right? For, let's say you were computing the difference in height of subjects between two populations, then it would be absolutely crucial to know the non-normalized effect size, because you don't actually care about the normalized effect size in some ways. You want to know the absolute measure, and if you're measuring something which is like a physical measure, you want the non-normalized effect size to be prominent in your analysis. In this instance, for fMRI data or for usually neuroimaging data, it's the non-normalized effect size is important. Or for instance, for anatomical data, right? Anatomical data, you do want to know what is the amount of volume that is the difference between the volume of the hippocampus between those two populations. You want to know the amount of volume. You don't actually want to know p-value on that. You want to say you want the error. You want to what's the range of error of that measurement, of course, but you do want to know the absolute value. Here, I'm in the context of where my noise is changing from experiment to experiment, and what is important is the normalized effect size. And again, this is the very simple formula that you can all remember So if you plot, and this is a simple plot of what's happening to the power as you increase or decrease the number of subjects, and you can probably guess, or we could almost guess from the formula, but it has to go through the density of the cumulative density function, so it's not that easy to represent. And let's say, and these are the that's interesting. Might work better. No? I don't know how to solve that problem. So let's read. Sorry, there's either something wrong with my charger or something wrong with it. Okay, perfect. Let's go to the source. So that's the kind of graph you would get by looking at the number of subjects versus the power. So if you make an experiment where the power is 50%, what does it mean? You're acquiring data. You have a lot of you're paying a lot of money to get those scanning time. Your own effort and all those things. What does it mean to have a power of 50%?
But you have a 50% chance of finding a true effect?
If the true effect exists.
If the effect is there, yes. If the effect is there, there's a 50% chance that I will find the effect. For a specific effect. Now, it does mean that I have also a 50% chance of not finding the effect. So what does it mean that to say, okay, I'm going to invest all this money, and I'm going to do all those things, and I've got half a chance of actually, if there is an effect, so let's say, it's maybe there's maybe there's 50% chance that there is an effect. And if there is an effect, I have only 50% chance of seeing it. Right? So that's a very poor, like you don't want to invest all this money for that little chance to get the results, right? To get to the truth. So that's the problem. The problem is that we are like globally in science, with all those 30 subjects experiments, are probably wasting a huge amount of millions, right? Because basically, even if we do get an effect, if you don't have the power, you're actually not sure what you're seeing. And So number of subjects for that specific experiment, power, you need like, so what was the setting again? We can look at the setting. So we're looking at the effect size going from 0.05 to 0.6, and then the number of subjects from 7 to 77, and then the alpha is 1 to the power of -3. So that means that for that, let's say I've taken this alpha because the often people threshold their statistical maps at that level, right? They want to see at that level what kind of a signal to have. So if I want 80% power, which is not unreasonable, I fall into the side of with a large effect size, with a very large, what I think is a large effect size, and you've seen in Ross' paper that there is actually a large effect size. Then you do have to have something like 50 subjects. How many experiments are done with 50 subjects? More and more, but as shown before, it's I think the median is still at something like 27 subjects. So we have a real problem, and it's a very simple computation. Like any first, if you start you doing stats in a first year stat, you would do this kind of computation. It's a very simple computation. There's nothing fancy. But it shows already that there is a big problem. Yeah.
But when we submit grants now, we have to do this. Like, at least in Europe, you will not get a grant accepted if you don't show exactly this calculation. Is it because people overestimate the effect?
Okay, so that will be some of the. Oh my God! Is it 4 o'clock? No way.
Yeah.
Okay. Well, I'll show you very briefly.
Yeah, I think that one.
So yeah, I completely miss. So I'll show you. I'll show you one thing very quickly because you can go through this little thing. But, that's, I think, my way of seeing the problem, and it's the problem of the overestimation of the effect size. So what you would do in a grant, you would look at the literature and try to work out what is the effect size, right? And there are not unreasonable ways of doing it. Like let's say you have a p-value. You go from the p-value. Let's say that p-value is from a z. Can be translated in one-to-one mapping to a z by the inverse survival function, and you go from p-value to z. So let's say you got p-value 10 to the -4, you get a z of 5. I don't know if that's the true right. And then you know roughly the number of subjects, so you can correct for the number of subjects, and then you have your covariance d. So you divide by the square root of the number of subjects, and you get the covariance d. And then that's a way of getting an effect size if you think that your experiment is going to give you the same sort of effect size. And then you could enter that effect size and look at what is the number of subjects that I need to get the effect size if I'm testing at that level of significance. That little simulation is just looking at each value on the x-axis is one experiment where I'm simulating 30 subjects or 50 subjects experiments, or looking at the difference between the two groups, and that's the true effect size. So I've taken the effect size, which is this one, right? The true effect size. But the detected effect, so for those experiments that showed some significance, on average, the detected effect will be much higher. So that's the blue thing here. So you detect the effect, an effect which is much higher, because simply you're just selecting those things that are significant. Right? By only selecting the things that are significant, you by definition detect effects that are higher than the true effect. Right? And this is so if you look at this little piece of code, it will show you how to, first of all, it will show you the confidence interval. It will see how you can compute the confidence interval on those things, and why. I mean, basically, this is just a very simple simulation showing you why the effect is overestimated. All right. There's a number of things from that I wanted to show you on the positive predictive value aspect, but which I don't know why I took my time and I haven't looked at the watch. The positive predictive value is an interesting aspect because you look at what is the prior on your hypothesis. So let's say you're thinking that this is a very crazy hypothesis. You have very little chance that this is a true hypothesis. Usually we'll do the experiment anyway because that's a very exciting experiment. But you'll have to know that if that experiment shows a significant test, you have to know that the probability of that experiment to be significant again the next time is kind of low because of its prior. So there's this, I think, not too complicated derivation of what is the positive predictive value, and I think and in that small derivation you'll see it's really not that difficult, and there's only two things you need for that. You need the Bayes theorem and you need the fact that probability of an event can be is the sum of the probability given the associated with another event. I can't remember but with those two things you can derive the positive predictive value very easily, which is the probability of a trade being true given the test. And I think I need to stop. I'm sorry that I took so long for so basic things, but remember, basic things like the p-value, they're not well understood. So spend some time, really understand, such that when your biologist friend or neurologist friend or the people you're working in your labs sort of like start to over-interpret the p-value, you can say, hey, no, this is not giving you evidence for the alternative. This is just giving you some sort of distance between the what you get and the null, and that doesn't take into account the prior on those hypotheses, and that doesn't take into account the alternative at all. Right. Thank you.
So just to relate what I'm about to talk to this, I'm going to talk about how you squeeze the most power out of your data as you can when you can't increase your sample size. So,
for a given sample size, how do you get most power?
it's for the clinical people out there. Well, it's for everybody, but